All right, why don't we begin? So today is the 24th lecture. We only have two more after this. So today's lecture we're going to continue our discussion on transformers. Hopefully we have a pretty good idea of what the architecture for transformers is like. And now, really, I just want to go over just, slightly more advanced methods when you're using transformer models, different transformer models, multi-layer, bursts, special tokens, that sort of thing. Okay? All right, so first thing I wanted to go over, last time we left off, first thing I want to go over, this is just code to load a model. So again, I'm pretty much just using Distill GPT-2 because it's lightweight and it runs on my CPU pretty well. IP progress not found. Please update Jupyter. Oh no, that's fine, right? Are you okay? Yeah. All right. Yeah. So that's just the model I'm loading every time. So first thing I wanted to do is talk about language generation. So last time we talked a lot about inference. We talked about generating text during an inference step. So we should talk more about it. So let's say we wanted to generate text, right? So last time we talked about generating text, and we said we start off with some particular prefix. The meaning of life is 2, and then we count on the model to fill in, right? So every time we put in a piece of text, what does the model do? It gives you a probability distribution among all the possible words in the vocabulary. So there are approximately, for Distill GPT-2, there's about 50,000 tokens. So for each of those 50,000 tokens, it will give you some probability, right? Some probability, and then you have to determine, based on those probabilities, what you choose the next word to be. So for instance, for this prefix, GPT-2 would give us the 3 highest probabilities it gives us words would be be, live, and say. And then, for instance, if we add b to the prefix, then the next most probable words for the meaning of life is to be are understood, able, a. The meaning of life is to be a, is to be a person, and so on. So this is sort of a decision tree, right? It's a Markov decision process. So the question is, what do we do? So the question is, how do we choose the next token, right? So last time we discussed, I gave you basically the very, very sort of basic, the basic generation scheme, which is you start off, and then at every sort of next step, we just choose the most probable token, right? So in this case, we start off with the meaning of life is 2, and then we have three. These are the 3 highest. I mean, you have 50,000 more branches coming out of here, but I don't think Graphviz could render that. So we choose the most probable token, which is B, and then next we have the meaning of life is to B, where we look at 50,000 more entries, but these are the 3 most probable, and it looks like 4.55 is the most probable there. So we choose that token, understood. So we have the meaning of life is to be understood, and then following that, we have the 50,000 tokens, the probabilities for each of the 50,000 tokens, and so on and so forth. Does that make sense? So each of these numbers, the way I've generated this particular tree is each of these numbers are a cumulative probability distribution. So I'm taking the cumulative log probability, because if I take the cumulative log probability, that's like taking the multiplicative probability across the series. Yep. So I'm just taking the sum of the log probability, and And this is where we end up. The meaning of life is to be understood as something, right? So on and so forth. I think the idea was to be understood as a whole or something like that. Very nice, very nice. But if we look at this graph a bit, the meaning of life is to be understood as is not actually the most probable sentence if we look at all the possibilities, right? For instance, the meaning of life is to be able to has a much lower probability. I mean, it has a much higher probability than the meaning of life is to be understood as, right? But we went down this branch, understood as, because the probability negative 4.5 is greater than probability negative 4.80, right? And because we went over that, because we chose this branch, we actually ended up in a less efficient, in a less probable state than if we went down this branch. But how could we know, right? At every step, we're just looking at the next step, right? Looking at every possibility 3, 4, 5 steps ahead of time is like infeasible, isn't it? Because it's an exponential increase in like possible tokens. This is just 3 of the highest probabilities at each step, but you would have 50,000. But even if you took only 3, you would have 9, it's 3, 9, 27. So looking 3 tokens ahead would require you to look at 27 possibilities. And that's not even to mention that why is looking 3 tokens ahead most probable? Why not look 4 or 5 tokens? I mean, we don't know. There's a chance that the meaning of life is to, and then whatever here would go up to negative, I don't know, 10, and then the meaning of life is to live in a thing would sort of stay around that negative 6 point, right? So really, we have a problem. We have a problem, which is that there's no good solution for this. There's no good solution here. We want to choose the most probable. We want to choose the most probable sentence. We want to choose a greedy method, but greedy methods, as you guys are probably well acquainted with, greedy methods often don't lead to optimal results. On the other hand, if we want to get the optimal results, that's computationally infeasible, just straight up, right? So, what do we do in this case? Well, there are 2 main options, and there's one probably more common than the other, which is to keep track of the top k possibilities at every iteration. Okay, so instead of having one path that you're greedily adding to, why not have 3, 4, 5, 10 paths, right? Now, is that ideal? Probably not. But it will give you some variety, and it hopefully could lead you down a path that you wouldn't have already led down in, right? So the way this works, for instance, let's initialize our model and say we have 3 possible outputs that we want to consider, okay? So the first step, the meaning of life is 2. When we look at the words, we just simply say, well, we have 3 possible outputs to store. We could store 3 possible strings. So we'll store the string, the meaning of life is to be. We'll store the string, the meaning of life is to live. And we'll store the string, the meaning of life is to stay. Because those are the highest probability strings that the model outputs so far. Okay? Then we have a choice. Then we have 3 possibilities. And then we generate 3 more possibilities for each of those outputs, right? We generate 3 more possibilities for each of those outputs. And for instance, for B, we generate the possibilities. The meaning of life is to be understood. The meaning of life is to be able. The meaning of life is to be A. And we calculate, again, the cumulative log probability. The cumulative log probability. Okay? And then for this beam, we'll do the same. We'll calculate the meaning of life is to live in. The meaning of life is to live, period. And the meaning of life is to live with, right? And we'll calculate the cumulative mean of those, the cumulative sum of those log probabilities, okay? And then with our final beam, again, we'll look at three possibilities. 3 roads our final beam could take. For the next path, we'll say the meaning of life is to say that, the meaning of life is to say comma, and the meaning of life is to say semicolon. Okay? And then we'll calculate the cumulative mean for those possibilities. Okay? And then once we have all of that, once we have three possibilities for each of the 3 beams, we don't want to, again, we can't store every single possibility. So what we'll do is just with these with these sums that we calculated, we could say, okay, what are the smallest sums? Well, the smallest sums is the largest sums is negative 4.5, negative 4.8, that makes sense, and negative 4.59. The beams, the outputs from this beam didn't amount to anything. They amounted to lower probabilities. So this beam will just travel right here. Okay? So we'll just sort of deactivate that beam and activate this beam to keep things going. Okay? And then we'll do the same thing again. Well, we have the meaning of life is to be understood. Then we'll calculate each of those 3 probabilities, calculate the cumulative log probability. Same thing here. The meaning of life is to be able to comma, and we'll calculate all those cumulative log probabilities. And we'll do the same thing here. The meaning of life is to live in and calculate those 3 probabilities. Okay? And then once we have those 9 values, then we just look to see which of those beams has the smallest, has the highest probability, has the highest log probability. So in this case, it would be the meaning of life is to be understood as, that's 6.4. The meaning of life is to be able to, that's negative 4.82. And the meaning of life is to live in a, that has negative 5.9. Everything else here, negative 6.39, negative 6.57, negative 8.69, negative 6.73. All of these are higher than those possibilities, right? So now, again, we'll just extend our beams those ways. Okay? So this is what's called beam search. It's called beam search because it's effectively, the idea is that you have a beam. If you have n beams, then you sort of just keep extending n beams to collect outputs of the lowest probability. And if a particular beam does not, if all the outputs of a particular beam do not have the lowest probability, then those outputs, then that beam transfers over to a beam that does have lower probabilities. Okay? So that's how beam search is used. So this is actually pretty much everyone that uses machine learning model. I mean, everyone that does large language modeling and text generation, pretty much you have to use beam search. It's pretty much a requirement. I will, just as an aside, I didn't put this in the slides, but there is one other way called top K results, which is basically you come out and you just calculate. So for instance, if we were calculating top 3, you calculate the top 3 tokens and then choose a path at random. That gives you sort of a more variable output. Typically, that's not desirable variability because you can't reproduce it. But you know, it is there. But yeah, beam search is very commonly used. So if we have some code, if we look at our code, oh, and no output. Okay, that it didn't generate. How could you possibly not? No mono. Oh, never mind. So the following 2 code segments are just to generate these trees. This is all written in Python. So if you want to play around with that, if you want to play around with how the beam starts, just to use this beam search tree function, just set the start text to whatever you want, and then it'll render some particular trees for you. That's using the GraphViz library. But I was looking for this function, which I wrote just in order to be able to visualize what beam search is doing. There we go. Oh, no. Yeah. Actually, let me get out of this. This view is terrible. There we go. So all this function does is literally it's manually calculating out the beam search. So for the number of steps in the max length of the beams, you simply calculate the next token logits, and then you calculate all the possible probabilities. Then you append the highest probabilities to each of the beams, and then you compress the beams. So you start out with 3 beams. You take 3 probabilities for each of those 3 beams, so you end up with 9 possibilities. Then again, you don't want to keep extending because that's an exponential curve. So after you look at those 9 possibilities, you compress those 9 possibilities back into 3 possibilities, 3 beams. Okay? So that's all this function is doing. And it just has like a little verbose thing that allows us to visualize it. So for instance here, we could see for the meaning of life is 2. For the prefix, the meaning of life is 2. It adds in be, or live, or say, for these, and it gives us these probabilities. Then the second step, the meaning of life is to be understood. The meaning of life is to live in something. The meaning of life is to be able. So this beam, the meaning of life is to be, got extended to understand and able to, and we abandon this beam, the meaning of life is to say, right? Mainly because the cumulative probability, the log probability after this token was added was all higher than the cumulative log probability after to be able was added. Okay, and then you sort of just go down the line. You go down the line, the meaning of life is to be able to, the meaning of life is to live in A, is to be understood as. You go down the line, the meaning of life is to be able to be, the meaning of life is to be able to live, the meaning of life is to be understood as A. The meaning of life is to be able to live in, the meaning of life is to be able to live with. Be able, the meaning of life is to be able to be 2. Meaning of life is to be able to live in A. Meaning of life is to be able to live in harmony. The meaning of life is to be able to live in harmony with. The meaning of life is to be able to be. The meaning of life is to be able to live, and so on and so forth. So you see what's happening. It's sort of starting to repeat, and then as it starts to repeat, there's one particular repetition that has a lower cumulative probability than the other sort of repetitions. And then that repetition, that cycle sucks in the other beams. Okay? So, not perfect. It doesn't solve core issues such as repetition with these models. I'm using a very simple model here. But, it does work for a while. It does work for a while. So there are ways to fight against this. You could try, there are ways to fight against repetition. The biggest is just use a different model that has an end token. I think that's the optimal way. There are options in the actual. Actually, I'll come back to that thought. So this is how beam search works. So the final beams is to be, the meaning of life is to be able, so on. Notice this is a different beam, this is a different result than with greedy search, right? The greedy search we talked about last time, the optimal sort of in the text generation was the meaning of life is to be understood as a whole, 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 right? So you have a very different text here. So you have a different cycle, basically. So both cycles have some log probability, and the truth is this cycle has a lower log probability than the other one. Yeah, so I know you guys enjoy hearing me say the meaning of life is to be able to, but in case you don't want to go through every single possible possibility, in case you don't want to go through every single possibility and you just want to sort of get to the point, and don't want to have to write beam search by hand every time, there's a transformers library. The transformers library, this is separate than like the normal PyTorch library. There's libraries for everything in Python, right? So the transformers library has a model generate function that sort of takes care of these things for you. And you could actually set the number. You could actually enable beam search by setting the number of beams to 3 or to a value larger than 1. Okay, and then you should be fine. What happens when you set the num beams to 1? Yeah, please. Yeah. Yep, that's just a greedy search. Yep. Beam search is still a greedy search. If beam search is still a greedy search, it's just sort of hedges its bets a bit, you know? So it's like a guy at the racetrack. You could have someone that's greedy and bet it all on one horse, or you could have someone that's still greedy, but you know, he's like, well, I'm just going to bet on a couple different horses, so there's more of a probability that I get what I want. Same thing. All right. Good. Yeah. So. Yeah, I mean, I set the max length to be fairly small, so you get 3 different beams. You set the max length to be larger. Again, you see we converge on sort of one text cycle. Okay. Does all that make sense? Any questions before we move on? All right, cool. So feel free to play around with these functions. Also the model.generate function has a lot of options, and it has a couple options with regard to like stopping repetition. There's like a max repetition and something else I forgot. I've never had luck with that. I honestly have tried so many times to use these like repetition suppressants in these functions with smaller models, and they have never worked for me. If anyone actually gets them working, sees an example of them working, I'd love to see it. But for me personally, I get the same result every single time. So feel free to play around with it. You know, I don't know everything about them, but yeah, that's why I didn't include it here. For me personally, it just never worked. It's easier to just get a larger model in an end token. Okay, so there we go. So let's go on to new subjects. Why is this fragment? Let's go on to new subjects, which is okay. I'm not going to play around with it too much. It appears much better on the website. So let's go on to the training. So with training, I didn't get to this, but training could be done. Well, I got to this I think 2 lectures ago. And so training is pretty simple. So we're going to talk about some different forms of training. But I want to jump in quickly and talk about basically standard training, because then a lot of other subjects depend on that. And then we'll come back to different forms of training towards the end of the lecture. And so training, literally, you could do the same type of training that we've done before with transformer models. So basically, we have a transformer model. We could have this is an encoder-decoder model. So for instance, let's say the task itself is Mary had 3 apples but ate 1. How many does she have now? I had this incorrect on the previous lecture. I corrected it now. But we could start off the output by sort of a prompt. I mean, really, the output we start off with by just saying start a sentence, right? Whenever you want sort of an answer from these encoder-decoder models, you just sort of, at the output, you put in the question in the encoder, and then at the output, you just sort of say start a sentence, and it should generate Mary has something. It should generate some English sentence. Still has an error. Oh well. So when we have this start a sentence, we give it a prefix, and then we put it through a decoder. So remember what the decoder does. It has a masks multi-head attention. Remember, half the attention is masked for the decoder, because we don't want the decoder to sort of be training on sentences. We don't want the beginning tokens of a sentence to be trained on the ending tokens of the sentence, right? So that's the issue here with the decoder. We want it to be unidirectional. We want it to have a one-way flow in time. Because when we have actual inference, it doesn't have the knowledge of future sentences to go off of, right? So if we're training on future tokens, and then we're modifying the weights on future tokens, and then during inference we don't have future tokens, it's going to just lead to bad results, right? So we give it, Mary has and then embedding, position encoding. Then it goes through a mass multi-head attention. A mass multi-head attention, just the different, like this is just half the attention network that of this, and then addition norm. And then we go through the cross attention, which takes in the output of the encoder, which gives you information of what the question is. It gives you, and then it takes in the output of the mass multi-head attention to basically basically tell the model, given the question, you need to pay attention to this part of the sentence, and then it adds that information to whatever it has before. It does a bunch of weights and stuff, and then eventually you lead to a probability distribution curve. Again, you're just generating a piece of text, one text at a time, and you get the next item, which is hopefully 2. Could be 1. Who knows? The LLMs aren't geniuses. They aren't stupid either. So you'll get some number. You'll get some number. You'll get some word. It could go 1. It could go 2. It could go banana. But every single word in the vocab list has a specific probability, and then it is up to you to figure out how to choose that probability, right? So in the case of actual training, we just do greedy decoding. There's no point in doing beam search or anything. So we just do, in training, we just do greedy decoding. So we just take the word with the highest probability and then append it here, and then hopefully move on keep generating text until we get to an end of sentence. Okay? So how do we train this? Well, we know what the output is supposed to be, okay? So for instance, with the question answering tasks, there are data sets that have the question and have the exact output of that question, that have literally, Mary has 2 apples, okay? So then you train it basically by every token. You compare the token to whatever the sentence of the output, in the data set is, and then do cross-entropy loss, right? That's simple as that. Now, is that perfect? Of course not. That is by far not perfect, mainly because, I mean, it's very possible the model wants to say it has the right answer. For instance, in this case, the model might want to say, well, thinking of this for a while, I want to consider that the possibility and blah, blah, blah. It might put in a bunch of preamble, but still come out and say, given all this information, I believe this woman has only 2 apples left. That's still the correct sentence, right? But it would still be marked as wrong, and we would still train the model to output the sentence, whatever the data set says. This is one of the hard things that you have to realize with how, when people see these large language models, they think like the way they're training, like there's some way that we're actually we're evaluating correctness in the way that I evaluate correctness on your exams, that I actually read your exams, and if it's the equivalent phrase, then I mark it as correct, and if it's not equivalent, then only then do I mark it wrong. That's not what we're doing here. This is a machine. We have a data set. We can't go through every single answer and say, well, this is correct, or this is mostly correct, or whatever. We just want the machine. We just have an input from the data set, and we want it to produce that output exactly. Yes?
No,
please.
With questions that are like this, like where it's like Mary had 3 apples at A1, there's like kind of logical questions.
Yeah.
I think about like large language models, like ChatGPT, you can ask it logical questions like that. Like you can ask it a complex math problem.
Yeah.
And it's able to give you like a precise answer. Is there like extra stuff in there in addition to the transformer for like doing that, like the sort of logical things, or is it purely just like a transformer, like the language?
So you mean just in general, or like with like OpenAI specifically, with ChatGPT, or like with modern?
In general, like if I ask ChatGPT like what's 73 plus 29, data on those like specific inputs.
Yeah, so yes and no. So the model, I mean, these models are huge, right? They're absolutely gigantic. So I mean, as 73 times 28, I mean, it probably hasn't come up a lot in our lives. But given the size of the data sets that OpenAI and OpenAI and Apple and Google are dealing with, it's probably somewhere in there. And there's actually a good body of research that shows that the larger, these LLMs are actually pretty terrible at generalizing addition and multiplication. If you make the numbers big enough, eventually their accuracy falls off a cliff. And it's likely because they don't see, like, no one really uses the numbers that are that big. So it's very likely that they are just memorizing. They're very intelligent parrots. The other thing to be aware of is that the very common, at least with like OpenAI, I mean, listen, I have no proof. So I don't have a proof of this. But with OpenAI and the commercial ones that you see that get super accurate results, there is a large body of literature on adding tools to language models to just help them be more accurate. So basically giving them Python. So I believe, I don't know what happened there. So I'm fairly certain, like given the research and given basically how far more advanced OpenAI is than basically things you see on Hugging Face, one of the things I think they're doing is basically when you ask the model a question like this, or just a mathematical question, it's very likely converting it to code and then evaluating the code and then spitting something out. So that's referred to as tool-enhanced language models. And there's a large body of research on it in the past like 3 or 4 years. So that's what they're doing. For simple things like this, I mean, I don't know what OpenAI does for simple things. I mean, usually if you train enough, the language model will get this. This will come up. For the advanced math and stuff, because I'm with you, the advanced math and stuff is incredible, the stuff it's able to come up with. And really, it's both a function of it has tools at its disposal, and what those tools exactly are isn't like released publicly. If you train on the models on Hugging Face, Facebook releases Llama a new version of Llama every year or two. If you evaluate those models, you will see that there is a stark in ChatGPT, what you get in ChatGPT, and what you get when you use Llama or Mistral or I don't know, T5 or any of these models that are on Hugging Face. And I think the biggest reason for that is ChatGPT basically includes all the tool uses and stuff with their models. The models on Hugging Face are literally just transformer models. It's just a bunch of weights that people download and get stuff out of, and they're far, far less impressive. So that's a big difference. Yeah. So this is very impressive. What you could do with an insane amount of data, and like this structure is very impressive. But also, even right now, I think your TA Niraj went to NIPS in December, and there was plenty of papers on just large language models just being terrible at math. Even ChatGPT being awful at math. And so really, it's a good trick. I know there's a lot of arguments on. There's a lot of. I mean, I'll get back to the lecture in a minute. But I know there's a lot of talk about will AI replace software engineers and stuff. And at least from my standpoint, when I try to make AI make a figure that requires precision and stuff, it just fails. It's not really good when I use it. It's much easier if I just make the figure myself. So I think all your jobs are safer now. I think this happened. Does anyone remember when Google Translate came out? It was late aughts. And it basically used like machine learning models and all of that. And when Google Translate came out, I mean, people were stunned. I remember this. I was like in college or maybe late high school. I remember people were going nuts being like, this is going to replace all the translators in the world. That job is completely useless now because we have Google Translate, and Google Translate works so well, we don't need translators anymore. So fast forward, God, it's almost 20 years now. there's still plenty of translators. All businesses like use translators. And the big reason is because while Google Translate works well, like 95% of the time, turns out that extra 5% is pretty important, right? It's the same reason why, you know, a lot of the robots or stuff that people are developing, even if self-driving cars work well 95% of the time, that extra 5% is the reason we need humans, not that 95%. So that's a long-winded way of saying, yeah, so the models are capable of logic, but as far as I know, there doesn't seem to be any real evidence that it's actually doing anything logical, you know. And so at least with arithmetic, it's very, like, if you keep increasing if you want to test out, keep increasing the numbers, and eventually it'll just fall off. The accuracy will fall off. And, so one thing I want to go on to is, before I leave this, is that when you read research papers, so for instance, with question answering tasks, right, there is a number that's correct here, like 2, right? They're going to give an accuracy number. How often did this model get this question right? And then, so how does it evaluate it? Well, no one's actually reading the output of the model and saying, okay, this is the correct answer. What they're doing is basically doing a search for 2. If they do a regex and see 2 come out of the model, then they mark it as correct. And if they don't see 2 come out of the model, then they don't mark it as correct. Now, is that 100% on the up and up? I don't think so. Like, right? The model could have been like, well, given, like, it could have just gone on a tangent on, like, oh, given the 2 people in this problem, John and Jake, and something, and in that case, 2 has nothing to do with the answer. It's just sort of saying some nonsense, right? But it would still get marked as correct. So one of the things to know when you're reading these research papers and you're reading sort of these accuracy numbers, like, just know that the accuracy numbers are rough. You know, in the spirit, no one could really go in and read every single output. So you need to have just sort of this shorthand. But most people don't think about what the sort of short accuracy estimate is. And if they knew, they would sort of be a little horrified. So at least with the question answering, all these questions, so if you look at GSM-AK, Grade School Math 8000, you have questions, you have sort of the answers that you train on, and then you have sort of a actual number that you need to search for in order to learn accuracy, in order to gauge if the model got something correct or not. Okay, all that makes sense? Okay, so as far as training goes, I just wanted to emphasize we train this model same exact way as we train any other model. We just get a bunch of probabilities at the output of the softmax function, and then we know what the actual token is supposed to be. We know the actual token is supposed to be 2, even though it says 1. We know the actual token is supposed to be 2, so we just have basically a vector we have a vector where each spot represents a vocab word, and then it's all 0, 0, 0, 0, 1. And then we compare that against the output of the transformer, the softmax, which will have probably not zeros or ones, probably have some very small numbers, and probably hopefully have a large number at the word 2. And then we compare that, and then do binary cross entropies, and then the PyTorch will take care of like implementing the gradient and shifting the weights in correspondence with the gradient. Does that make sense? So I know we're getting a little bit more abstract more and more as we go on more and more, but literally I want to emphasize this. I can't emphasize this enough. It's not impressive. We've done this. It's just doing things at a bigger scale and more automatically. Okay? All right. So, okay, so one other minor thing I wanted to touch upon, I talked about this a little bit last lecture, but wanted to touch about it again, is that many models use special tokens. So for instance, in the mini LM model, I think this is a Microsoft model. Yeah, I'm pretty sure this is a Microsoft model. I'm not sure why it's not hosted by Microsoft anymore, but it is a Microsoft model. When you tokenize the student graduated with honors, you get a bunch of special tokens in it. Studious, that's a special. The studious student graduated with honors, and then period, and then separation. Oh yeah. Okay. So basically, this model's tokenizer inserts a whole bunch of tokens into the sentence, okay? So the big thing it inserts is the CLS token and the separation token. What are the CLS token? The CLS token is short for a classification token. It's inserted, like most models, insert it at the start of every input, and it's used as a sentence representation token. So the CLS token is one, if you want to do something like sentiment analysis, if you have something where you want to classify a sentence as a binary variable, right? You attach that binary variable to a linear net, and then, I mean, you have to attach something to like a network and then get something out, right? So instead of attaching all the tokens to a linear network and doing a whole bunch of other nonsense, what people typically do is attach the CLS network to that feed-forward network and then softmax it to a 1 or 0. Okay? So what does the CLS token do? In this case, the model learns that the CLS token is supposed to absorb all the information of the rest of the sentence segment. So that's why, so when you use one particular token for sentence classification, it's important to have that one token, so have an extra token that sort of absorbs the information about the rest of the text. Okay? So that's the idea behind the CLS token. We'll see an example of that in a minute. The sep token is a separator. The sep is a separator token is just it's inserted between two sentences or between any like two segments, I guess. I've seen it inserted in between, for certain tokenizers, inserted in between like equation and text, stuff like that. Again, it's just one of those things that, you know, you're giving the model more information, ideally. And hopefully the model is better able to process the information if you give it more information. It better process a sentence if you give it more information. So does it work? I mean, I don't know. The people that designed the model thought it did, so that's why they put it in there. But that's basically what it's doing. As far as CLS goes, we're going to talk about BERT a little bit more in just a moment. But again, I just want to emphasize that BERT is just a transformer model. You can think of this as an encoder. So we pass in a particular sentence, starting with the CLS token, into this. And then at the output, remember, when we go in the encoder, with the encoder, the output has the same dimensions as the input, right? So the output has the same dimensions as the input, and every one of these spots corresponds to the probability of what the next token, of the probability distribution of what the next token should be, assume what the next token should be after this token, right? So this little thing right here, this output right here, corresponds, this vector output right here corresponds to the probability distribution of what should come after help, okay? So if we didn't have any special tokens, and just put this out, then the question is, if we want to classify a sentence as positive or negative, what token should we actually attach it to? Or should we attach it to one token, or should we attach it to all of it? It's not really useful. It's not really useful. I mean, there is a train of thought that you could attach it to all the words. You could attach to all. You could do a very large classifier, attach it to all the words, and do that. But you're not really using the transformer attention if you do that, because you're basically just reducing all of this to a linear layer classifier. So in order to use all this special attention stuff in the transformer, basically you just send in an extra token, and then when you want information, when you want to use information about the text to do something, for instance, spam or not spam, you could simply say to your model, say to your code that the model, this token attaches to a classifier network and puts out a 0 or 1, and then you do binary cross entropy on the output of this classifier. Then this gradient back propagates into the transformer encoder, and the transformer learns that, okay, this token is the important one, so I got to make sure this token represents what's in the sentence so far, what's in the rest of the sentence. Okay? Yes.
So kind of where
Yeah,
fact
please.
that it uses the CLS at the very beginning of the sentence.
Okay, yeah.
Does it, would it not be better to feed like the sentence through the transformer and then have the token after the sentence be the classifier?
Oh, that's such a good thought. That's such a good thought. Doesn't matter. I'll ask you that. Doesn't matter.
Because I guess I'm still thinking about this from from an RNN perspective,
Yeah.
where the order of the inputs we feed in affects the results.
Yeah.
Isn't that the same thing with the transformer because there's a positional encoding?
So there is a positional encoding, but each of the positional encoding, so the positional encoding is added to the token. So because the positional encoding is added to the token, we could flip these tokens around. But as long as we keep that positional encoding the same for each token, then the model will still see everything the same. You know? So it'll still see, so if the positional encoding here is 2 is help, 3 is prince, 3 is Mayuku, then we could flip these around. The actual sort of, we could flip the actual connections around. But still, 2 will be attached to help, even if help is over here. So the model will just learn, so the model isn't looking necessarily for what is attached in this space. It's just looking at what's the token, what's the positional value. So from that standpoint, that's one of the nice things about the transformers, and that's one of the advantages over the RNN. It's sort of position agnostic. Okay? And that's what you want, because depending on how big your sentence is or how small your sentence is, you don't want it to sort of you don't want it to give more weight toward the beginning than towards the end, because if you have an especially long piece of text, then the long pieces of text will suffer, because then only their beginnings will be considered, right? So you want the transformer to be agnostic of its own weights. You want it just to be able to do calculations on whatever is inputted into it. But you still want to be able to flip the wires. As long as the data is the same, you want it to do the same thing. Does that make sense?
Then it doesn't matter basically where you put the CLS.
Yeah, it doesn't matter. Yeah, yeah, it doesn't matter. Yeah, so I mean, if you wanted to, I mean, the CLS putting it at 0 is really good, because also the sentence is variable length, right? So the sentence is variable length. So if you put it at the end of the sentence, then you would never really know where the CLS token is. So then it makes training the model and all of that like constructing this whole system, it makes that a little more difficult. Not impossible, but just not straightforward. Does that make sense? Okay. So yeah, so that's the CLS token. Let's see. Training flexibility, what was it? Pooling, here's the reason. Oh yeah, so basically I wanted to, I mean, you already asked that. Ben. So yeah, so the reason we included is training flexibility, attention mechanism, pooling, multi-segment inputs, pre-training, fine-tuning. It's basically just a token that's there to, it's a token that's there to basically capture the information about the entirety of the segment, and then be used for whatever task, you know? And so there's all sorts of tasks that you have. Sentiment classification, spam, not spam. You know, even things like question answering and stuff. That it might be useful for that too. Okay. Yeah. So it has its own. So it's a token. Like it's literally a token, like any other word. Has its own embedding. Has its own embedding. Has its own hidden states. Interacts dynamically with interacts with the attention, and basically it becomes a summary vector. As long as the model learns to make it one. So the training is the trick there. All that makes sense? Yep. Okay, so as far as special tokens, there's lots of them. We're going to talk a bit more about BERT, but BERT has CLS, has SEP, has PAD, mask, unknown. Roberta has other tokens. It uses the angle brackets. GPT-2 has no explicit special tokens. That was one of the things that OpenAI was a little late to the game on. No special tokens. So that's one of the reasons why it's so susceptible to repetition, because it has no end of sentence token. That's a problem. Yeah, T5 is another model. It has its own special tokens. Yeah, so one of the frustrating things about life is that the more you get towards the bleeding edge, the closer you get towards the bleeding edge, the less things are well defined, and then you just sort of have to roll with it. People make decisions, and then eventually someone will win. Eventually, one of these systems will win. More people will adopt it than not adopt it, but we got to wait a couple decades for that. You know. So up until then, whenever you're using these different models, you have to go into the tokenizer and learn what are the special tokens in these models and which tokens should you use for your particular task. Yeah, so CLS, beginning of sentence, end of sentence, etc. Yeah, so you look it up. Okay, some other minor things. We're just going to run through some minor things about transformers. Layers, transformer layers. Remember, recurrent neural networks. Remember what layer we had in recurrent neural networks. We had layers. So how did layers look in RNNs? It was simply you had one RNN, and then it gave out an output, and then that output went to another RNN, right? How do you think layers in a transformer work?
Put the output on one model so then it's just output.
Yep, just one output to the other. So, I mean, of course, there is an encoder and decoder in transformers. So typically, the way layers in transformers work, the encoder feeds into another encoder, feeds into another encoder, feeds into another encoder, feeds into another encoder. Decoders are the same way. The only slight subtlety here is that you have cross attention. If you have an encoder-decoder model, you have cross attention, right? So what should you do? Well, the typical thing to do is simply to feed the output of the last encoder into the cross attentions of all the decoders. Basically, give all the decoders the same cross attention from the last output of the encoder. This seems to be what people use. I know some of you are thinking, why can't we put the output of the first encoder into the cross attention of the first decoder, make it more ladder symmetric? There is a paper on this. I forgot to include it in the slides, so if someone wants to remind me on Piazza, there is a paper that does this, but it doesn't seem to have caught on, and it's computationally more expensive. So I think people just this works. This is one of those things that works. So this is just typically what people do. So when you load a model, and when you load a model, you load the outputs or logits, you're gonna typically have to select between layers. Just know that this is how everything's structured. Okay, nothing special. It's just something that's not clearly explained on the internet, so I wanted to put it here. Bidirectionality. We have RNNs are bidirectional, right? Basically, we had a RNN. We trained RNNs by having a forward RNN, putting tokens in a forward fashion. We had a backward RNN, putting tokens in a backward fashion, and then we put those combined outputs of those two to get a new output, right? That was a bidirectional RNN. So, what does a bidirectional transformer look like? What do you guys think a bidirectional transformer looks like? I mean, this has already been spoiled, but I'll see who's paying attention. What does a bidirectional transformer look like? Yeah.
But I'm curious how mass detention works.
Oh, perfect.
We don't want it to cheat, but now it's being explicitly given the end of the sentence.
Oh, perfect. Okay, good. So, oh, perfect. You caught it. Okay, so why is this formatting not working? Oh, how is this not there? So in the transformer model, the encoder is bidirectional, right? Transformer models take in all the tokens at once. It's not like an RNN that has to wait on each token, right? One step at a time. Transformers take all the tokens in at once, and then the attention, at least in the encoder, the encoder is bidirectional because attention is calculated because you have an attention head, and the attention is calculated for all tokens everywhere, right? It's all crisscrossed, right? So an encoder is bidirectional. But the decoder is not bidirectional. The decoder is not bidirectional because you have that mass multi-head attention, because we're specifically telling the transformer that we do not want you to be bidirectional. We want you to generate something one token at a time. Okay, so you have this mix. So depending on what your language model looks like, it might be bidirectional or it might not be bidirectional. And so now is a good time to tell you guys that you don't necessarily have to use an encoder-decoder representation for your language models. In fact, most language models are not the combination of these two things. There are language models that are one or the other. So BERT itself, BERT stands for bidirectional encoder representations from transformers. BERT is probably the OG large language models that exist, okay? It is one of the first transformer large language models that was released. So what is BERT? BERT is literally an encoder-only architecture. It is a layered encoder-only architecture, and the input is, it takes an entire sequence of tokens at once, and it has a self-attention, and then the output is it produces embeddings for all input tokens simultaneously, okay? And so as we discussed, it has that CLS token, so if we want to do some sentiment classification, we do that. But it is a encoder-only network. So here's the rub. Because BERT is an encoder-only network, it does not generate text, right? But it is still a large language model. It could still do other NLP tasks. It could do sentiment classification. It could do, it might be able to do some form of question and answering if you constrain the question, if you constrain the answer in a certain way. So here is where we're getting sort of a bifurcating of the language models. We are getting language models that do some specialized tasks that are basically built to process text and give out yes, no, etc. Give out some classification outputs. And then you have language models that take in text and are meant to generate more text. Okay? So BERT is a former. BERT is simply a language model that takes in a sentence and needs to process it. Just understand it. And it gives out some classification for it. Spam, not spam. Yes, no. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That sort of thing. Okay? So in that case, BERT is an example of an encoder-only architecture. And because it is encoder-only, because it uses a standard encoder from Viswani, then it is bidirectional. Does that make sense? So BERT, so what else do I have? So as far as training BERT, now is a good time to come back to training because we need to be able to train this, right? So I showed you last time training a model. You could do it like with question and answering and all of that. You could train it directly, right? You get an input, and then you want a certain sequence of tokens at an output, and you just do sort of a cross entropy training directly. That's great, but most of these models, the thing is, we don't want to have a different model for every single task, right? We don't want to have to train a new transformer model for every single task that exists. We want what's known as a pre-trained model. We want a model that basically could understand English, outputs something, and then in order to do a specific task, we could just slap a feed-forward neural network and some softmax on it, and then get some particular output, right? That's what we want. We want basically the whole understanding English part out of our hands, because the understanding English part is a huge amount of data and time. It's a huge amount of data. The only people that could do that are Google, are Apple and stuff. And it takes a shocking amount of electricity and servers to do that. So we want to be able to train the model to understand English, to understand language in an unsupervised manner, because we don't have labeled data sets. And so the question is, how do we train a model on language unsupervised? Okay? So the two big methods I'm going to show you in this lecture is one is called mass language modeling. In mass language modeling, you just take an input sequence. You know, you just scrape Wikipedia, get a bunch of sentences, and then you input that sentence into the model, but instead of inputting all the tokens into the model, some of the tokens you replace with a mask token. So for some of the models, the embedding is for mask that gets inputted, and for the other sentences, that is fine. And then what you do is basically you attach a feed-forward softmax at the end of the transformer, and then you force the model to output what the original word should have been. Okay? So the model learns that when it sees a mask token, it's supposed to output the embedding that corresponds to a particular word. Okay? So I know it seems weird. I know it seems weird because, like, why should this work? But the reason it works is because you're asking the model, basically, to look at the spaces in its input and look at the surrounding text. And then based off the surrounding text, you want it to estimate what the actual, you want it to guess what the actual word missing there was. So for instance, like for us particularly, like as a human being, if we see that blank there and we say the quick brown, something jumps over the lazy dog, we would guess probably an animal, right? That's because we understand language, right? Model has to do the same thing, right? That's how it's being trained. And so it turns out if we're doing that, if we keep doing that mass language model over enough text, it sort of starts to understand English. Makes sense. Makes sense. Seems simple, but it is strangely effective. This, by the way, is not an original thought. It's a thought that was introduced with word embeddings, with word-to-vec, right? But they extended it to work with transformers, which is pretty spectacular. So that was one of the innovations of BERT. This is just training. This is just some code to train with. I just wanted to say that mass language modeling, you could do it automatically. And so there is a trainer object that allows you to do that automatically. The other method to train language in your transformer model is next sentence prediction. This is probably what I would have gone with first. But apparently mass language modeling works better. And sentence prediction is similar to mass language next sentence prediction. It basically works by taking two sentences, inputting two sentences into the model, and then inputting by having a pair of sentences that are similar. So for instance, that are related. He went to the store, he bought some milk. Those two things are related. We could input that into the model, and the model is supposed to see that they're related. Similarly, what if we input two sentences, he went to the store, the Eiffel Tower is in Paris. Those two things are not related. So we have the model take in these, if the model takes in these two sentences, it's supposed to output that they're not related. So forcing the model to identify whether two sentences are related or two sentences are not related also forces the model to learn language, right? It's basically, again, a classification task, except now the classification is these two things are related, these two things are not related. Last couple minutes. So good. So general purpose, so as far as that, BERT is an encoder-only model. A decoder-only model is what we are very acclimated with, which is a general purpose transformer. It is a decoder. It is a decoder-only architecture. That is what OpenAI uses. That is most language generation models in use today. They are decoder-only. Basically, you just have the decoder. And so the question is, if you don't have an encoder, how do you have the cross attention with the decoder? And the answer is you don't. You just remove the cross attention from the decoder, and you just move on. So decoder-only models. Decoder-only models are useful because you need them. You need decoders to generate text. And it turns out, for a lot of stuff, I mean, you can make the decoder just huge. You don't necessarily need the encoder. So that's something. But what is important is that with decoder-only models, they are not bidirectional. Okay, so they're not as good for things like classification and that sort of thing. They are good for generation. Encoder models work for classification tasks. Decoder-only models work for generation tasks. And so, like BERT is an example of encoder-only model. GPT is an example of decoder-only models. There are examples of models that have both, that are sort of a hybrid of both, that you could do more tasks with, that you could do a greater variety of tasks with. The T5 is an example of that. But people are just releasing models. So you just got to figure out what model works best for you. Okay, and so that's a good place to end. So homework 10 is due Monday. Midterm is next Thursday. The skill science cheat sheet will be out by today. I'm gonna release the sample. I'm gonna wait till the weekend to release the sample because we're still debating 1 or 2 questions on the midterm, and I want to make the sample similar midterm, not exactly the same, but I want it to be representative. Okay, I'm not promising it's exactly the same. So I just want an extra day or two to, if there's a question that I'm going to drop from the midterm, I want to drop it from the sample too. So, so give me till the weekend. And so that's going to come out, and most importantly, have a good weekend. All right, guys, thank you. Yeah, please.